All right, we're back with today's essential question. How can we solve problems involving two-slit and multiple slit interference? And so interference we'll define as when coherent waves meet, a repeating pattern of points of reinforcement and cancellation result. So that's like an interference pattern. We know that waves interfere, so when we see interference, it gives us a clue that that might be a wave. For two-slit interference, I've kind of sketched that out on the board right here. So we have laser light with a given wavelength. I've chosen red, 700 nanometers. There'll be a certain distance in between the two slits. We call that A. There's a distance between sort of the two slit and the screen where we're observing the interference. So here is where we'd observe the interference pattern. And that's what I kind of want to take some time to explain right now. So the light that's emerging from each of these slits, the laser light that sort of passes through, it's going to spread out, right? So diffraction is when a wave passes through a narrow opening or sort of bends around a barrier. And so the wave that's coming from this slit is spreading out like this. And the wave that's coming through this slit is spreading out like that. And so there is a region sort of right here where those two waves are meeting, or they're overlapping. So that's where we'll observe interference. We would not observe interference up here or down here because only sort of one of the waves is getting there. We need the two waves to superpose, to overlap, to meet, to see that interference. So what's going on there? Both waves travel the exact same distance to go from this slit or this slit to the midpoint sort of in between them, right? So it's equidistant from here to here, here to here. And we could say, like, how many wavelengths have sort of, how's the red light sort of, oscillated through to get from here to here would depend on the distance d. So if we just choose a value like 1 meter, and we put, a laser 1 meter away from our collecting screen, and we did this, and we said, well, the wavelength is 700 nanometers. That's billions of oscillations, right, to get from here to here. In other words, that's a really tiny wavelength. And so if we have 1 meter divided by 700 nanometers, what would that give us? Let me get my calculator. In other words, how many entire wavelengths for that red light would fit in between the two slits and the screen we're observing? So we have our 1 meter. That's what I'm choosing for D, divided by 700 times 10 to the -9 is nano. It's going to be about 1,428,571 oscillations. So there's going to be sort of 1.5 million wavelengths to get from here to here, but the same number from this one, right? Exactly 1.5 million to get from there to there. Exactly 1.5, but exactly the same as this one. And that ensures that at this point, we're going to get constructive interference. They've traveled the same distance, and so their phase difference is 0. They're in phase. Their path difference is 0. There's no difference in their path. Okay, so they've traveled the exact same distance. If we move off of this bright point, again, it sort of lines up with the midpoint between the two slits. If we go off of it a little bit, and let's think about, and I'm not going to draw all 1,420,000 of them, but let's just sort of say the light that came from here, had to go a certain distance to get there. The light that came from here didn't have to go as far. Okay, so we get to a point above sort of the bright fringe where the wave that has had to go further has had to go a whole half a wavelength further. And so that by the time, let's say there was a crest from this wave there, it would be like a trough, from this wave. So the trough would sort of, meet it from that one. And so there's an example of destructive interference where crest meets trough. And so this is going to be a dark spot. Destructive interference. Bright spots occur, that's the reinforcement, right? Where crest meets crest, trough meets trough. Here is where the crest is meeting the trough, right? So it's canceling it out. And if we still move off from that point a little bit further, we'll find there is another bright spot. because at that point, the waves have had to go longer still, right? So that the wave that's coming from this bottom slit still has had to travel longer than this wave, but it's had to go in full wavelength longer. So now the path difference is one wavelength. And so when the path difference is an integer multiple, it's the path difference here is 0. The next bright spot, the path difference will be 1. Remember, the path difference just sort of tells us the difference in the path, the wavelength. The phase difference is like talking about how there's 360 degrees of phase or 2 pi radians of phase. So we can express sort of if the waves are coherent, okay, in terms of they have a constant phase difference or a constant path difference. If the path difference is 0 or 1, here there'd be another bright spot sort of down here, which is also going to be 1, but it's sort of now this one's how to go the extra wavelength, right? The dark places are when the path difference is a half a wavelength. So the dark spot, we have a path difference of half a wavelength or 1.5 wavelengths. So anytime it's an integer multiple, that's where we're going to find the constructive interference, the points of reinforcement. Every time when we see a point of cancellation, that's going to be when the path difference is half a wavelength, off. And so 1.5 or 1.5 or 2.5 or and so on. So that means that one wave has had to move a whole extra half a wavelength, ensuring that the crest is going to be the trough, and that's why constructive interference. Okay. So x is the distance between two. Okay, that's what that is. So this is just purely sort of geometric in terms of the mathematics. We're relating lengths. So wavelength is a length, it's the length of the light, and that's related to the distance between the slits A, the distance between the bright fringes X, and the distance from the two slits to the board to the screen where we're observing the interference is D. And so it's just sort of some geometry there. This is the equation that helps you solve problems involving two-slit interference. You may have to solve for the wavelength, or for A, or for X, or for D, for any of them, right? But you'd be given enough information to solve for the other three. So 4 variables related in this equation. In order to solve it, you have to be given 3 of them, right? So just kind of make sure you know what each one stands for, so that when you are solving problems involving two-slit interference, you can size it up correctly. Lots of chances for conversions, because wavelength is usually visible light in nanometers. The distance D is usually in meters, because this is something we set up in a laboratory where we don't have like a nano scale lab to do these experiments at. So kind of keep that in mind, usually conversions there. Multiple slit interference, you may recall, has a different equation that's helpful, and that's the one D sine theta equals n lambda. Lambda is still wavelength. N is the order number. Okay. Theta is the angle that the light is being diffracted, and D is the distance between each of the slits. And so here's like we've got, let's make it a green laser now. Instead of sending it through 2 slits, we're going to send it through like a whole bunch of them. Multiple slit interference. And so you have the same thing. You have a bunch of waves that are spreading out, and they're all going to overlap, and they're all going to interfere. And so you really see the same exact thing in interference pattern, but the fringes are sharper. They're more clearly sort of, spaced, because you've got a lot of waves that are sort of piling up to sort of add to that. So D is just, it's similar to A. It's the distance between sort of any 2 lines. Sometimes you're going to be given information like N, here's the number of lines per millimeter. And we have to recognize that the distance between them is going to be 1 over that. Or the distance between lines is going to be 1 over N. So 1 over D is N, or D is 1 over N. Where N would be the number of lines, say, per millimeter. So some of the ways that you're sort of given questions, and we'll see some examples here in a moment. I might say a diffraction grading with 5,000 lines per millimeter, right? So it's telling you N equals 5,000 lines per millimeter. So it's not really telling you the distance between each one. It's telling you this is how many there are in a millimeter. So if we take the inverse of that, then there's 1 millimeter per 5,000 lines, and you just divide by 5,000, right? And you have the number of millimeters here, which you can convert into meters. So that's one wrinkle in the diffraction grading equation, where they don't always give you D. Okay, they might ask you to solve for n or for lambda, you know, and they give you n, and you have to turn that into D, the distance between each line on the diffraction grades, which I might just put on the whiteboard over there to spell all this out. Theta cannot be greater than 90 degrees. Okay. And you can kind of like prove that to yourself in the calculator. Like you can't do anything, you know, sine 90, right? Sort of maximizes that term. So we look at a diffraction grading, and let's say it's like white light. We're going to split the white light up according to the wavelength. So like red light diffracts the most because it has the greatest wavelength. Purple light diffracts the least. Angle theta. So it's really the angle theta from sort of the zero order, which is analogous to this point directly sort of across the midpoint there. There's going to be a zero order maxima. And then you'll see a certain number of orders, okay, either above or below the zero order, right? And that's just like how many interference patterns could be observed there, or to what order n is a way of being diffracted, you know, an angle theta there. So I'll kind of leave all this here, I guess, and we'll say, that's all right. So here it's like we've got our screen, we're going to have the zero order right here, and then there's going to be an angle theta that brings us to the first order. There's going to be a different angle theta, right? Theta 2 that brought us to the second order. There could be 3 or 4, however many. So there's order numbers both below the zero order, and there's going to be sort of above the zero order. 1, 2. And so for a given order n, there is an angle theta that light has been diffracted to, and it's governed by this equation. So the bigger the wavelength, the bigger the angle for a given diffraction grading, with, you know, n number of lines per millimeter, which is a distance d in meters between each one, to a given order. Okay. I mentioned before when we sort of first introduced this that a very typical question that they ask about this is to sort of count how many orders would be visible. So it's kind of like, if we set up a situation where we're diffracting, let's say white light, it's going to diffract into all the colors of the rainbow. And we want to select how many little rainbow spots would we see, or like how many, you know, how many total images sort of will we see of whatever it is that we're, you know, sort of looking at. And so the path to the solution there is to use they're going to give you enough information to, you know, plug in for D. If they don't give you D directly, they would give you N. You calculate, you know, 1 over N is D, make sure it's in meters. They give you the wavelength. And you have to plug in 90 degrees for theta. You have to know that that's the maximum, that sort of maximizes this term. You can kind of think about it like, from here, there's no way for it to diffract more than like that. Right, it's like we're measuring relative to the zero order, so a 90-degree diffraction would be the light sort of all the way down like this, and we're not going to see an order sort of down there. So, but yet that maximizes it. So 90 degrees gets substituted in, and you solve for n. Keep in mind, if you're solving for whatever n was down here, like close to that 90 degree, whatever, you know, sort of order you'll get to. So let's say it's 3, or let's say it's 3.4 or something. You solve this, you get n equals 3.4. Well, you got to round it down. You can't have 0.4 orders, so it's the whole number. And you'd say, okay, there would have been 1, 2, 3 orders on this side, which means there's 1, 2, 3 orders on that side, plus the zero order. So when you solve that for n, but the question is saying, how many images will we see? You know, something like that. How many interference, you know, fringes will be observed? You got to double n to account for the order number on the other side of the zero order, and then you got add one to add in the zero order itself. And so usually, you know, you'll have those other incorrect answers as an answer choice on like paper one. You got to be able to, you know, double n and add one to it. You know, round it down, double it, and add one to your answering a question like that. So that's how you would solve a problem involving multiple slit interference, right? You're going to use this equation. So multiple slit, you design an equation to help you with diffraction grading. Design diffraction grading. Two slit, this one, lambda equals ax over z. And you gotta know what each one stands for. Let's look at an example of like practice problems involving these ideas.